before we continue with the physics part, let me ask you if you thought about these three terms here. So any thoughts of what is the physical meaning of any of the three? Yeah. Yeah. So yeah. So so my question for you is: any thoughts of what is the physical meaning of any of those three terms? You can choose any of the three.
This is up to you.
Yeah.
So the first one, it's like speed.
And physically, what is it? Yeah, what symmetry it breaks, maybe some material that realizes it, or what does it mean in real space, or what does it mean physically?
Removing the spin, the electron spin into a level and flipping it.
Yes.
Creating it again.
Yes. All right. So, is this a magnet? So, does it break time reversal symmetry? For example? So, anybody that thinks that it doesn't break? Yes, this term breaks time reversal symmetry. And this is just, for example, an in-plane magnetization. So you can think about chromium chlorine, for example, or nickel iodine. Their mean field has many terms like this. So let's move on to the next term. So this one, it's very, very similar to this one, but instead of n plus 1. So my question for you is, does this one break time reversal symmetry? Yeah. Yeah, it could break translational symmetry. It doesn't have to. And also it could break time reversal symmetry, but it doesn't have to. This one has to break time reversal symmetries. This one doesn't have to. Yeah.
So the one on the right will break. No, it's the same.
At least that the one in the center can come back.
Yeah, so I mean, this is one term. Of course, you have the Hermitian conjugate as well. And of course, for this one, you also have the Hermitian conjugate. So does this term have to break time reversal symmetry? It could, but it doesn't have to. So this term, it's also spin orbit coupling. So this is the term that you have in systems that have, for example, Rashba spin orbit coupling. So when you put a two-dimensional material on a surface, and this term doesn't have to break time reversal symmetry. So let's move on to the last one. So any thoughts of what this last one is? Any thoughts on what it's not? No, in principle, no, right? Magnetism should be creation. No.
What it is not.
Yeah, it's not magnetism. It may be a little bit related, but it's not magnetism. Yes, that's very good. It doesn't conserve charge. That's a very good clue. So, any thoughts? Yes, this is a superconducting term. It's certainly a superconducting term, but you remember that usually we had up and down for superconductivity, and this is up and up, right? So this is superconductivity, but this is unconventional superconductivity. And this is, for example, the term that you get when you put chromium bromide on top of niobium diselenite that realizes an unconventional superconductor. And that is something that we are going to address tomorrow. So all these three terms are going to appear over and over and over in the next few lectures, and also, of course, in the exercise sessions. So here we have in-plane magnetism, spin orbit coupling, and unconventional superconductivity.
Could you remind me what you mean by N? Is it the lattice side or
yeah, it indexes an orbital or a lattice site.
Okay.
Yeah. So first index is orbital or lattice site. Second index is the spin index. So we assume that we have both spin up and down in every single site in the lattice. All right, great, wonderful. So let us now move on to some very specific two-dimensional materials. And now that we know both, let's say, electronic structure, mean field, second quantization, let's start with the simplest two-dimensional material, which is graphene. So the basic idea is that for this whole course, we will try to focus on understanding the electronic properties of two-dimensional materials using minimal tie-bonding models. Namely, that we will not aim at doing full quantum chemistry calculations with all the orbitals and with exchange correlation functionals and so forth, but rather at thinking about what are the lowest energy degrees of freedom in two-dimensional materials and building models that describe how electrons behave in these lowest degrees of freedom. And for example, graphene is one of the best examples of this. So in graphene, in principle, you of course have carbon atoms, and carbon atoms have both s and p orbitals, and in particular 3p orbital, right? So you in principle would have an s orbital and px, py, pc orbital for every single carbon atom. The magic of graphene is that due to the symmetries that it has, the pc manifold, namely the electrons that live in the pc orbital of carbon, are electronically decoupled from all the orbitals that all the other orbitals that you have in graphene, and in particular, all the low energy properties of graphene are accounted for this by this pc orbital. So in particular, for graphene, you get a nearly perfect low energy model just by taking a single orbital per carbon site, an orbital that it's a pc orbital, and considering just first neighbor hopping and maybe second neighbor and third neighbor hopping between the different carbon sites. So for simplicity, let us just take first neighbor hopping, but then in the exercises, you will see what happens if you introduce second neighbor, third neighbor, fourth neighbor, and so forth. You will see what is the impact of this in the electronic structure. So if you take just this minimal tie-bonding model, one single orbital per carbon site with first neighbor hopping, then the electronic structure that you get is essentially this one. So the x-axis is the momentum, is essentially the block wave vector that we take in some path in the two-dimensional prolonged zone. It's not important exactly which path, but what is important is that the chemical potential in graphene lies at zero energy, and this chemical potential intersects the band structure right in two different points that have a Dirac cone dispersion. So these 2 points here and there are the Dirac points of graphene that essentially account for all the low energy properties that graphene has. So in particular, one of the typical things that you can do with this tie-bonding model of graphene is looking at how the Fermi surface looks like. So if you have an undoped monolayer of graphene, essentially your Fermi surface only intersects zero energy at this point and this other point, and therefore your Fermi surface is just 2 points. And these 2 points here are the K point in the Brillouin zone and the K prime point in the Brillouin zone, the points where your Dirac cones lie. And then as you increase the chemical potential, then you start having finite Fermi surfaces with a radius that gets bigger and bigger and bigger as you increase the chemical potential more and more and more. And eventually, once the chemical potential is very large, much larger than what we can usually achieve in experiment just with electric gating, then one reaches something called a Van Hoff singularity, a state in which all your Fermi surfaces merge and the topology of your Fermi surface changes. So let me emphasize that this kind of Fermi surface for graphene is not realistic, at least if you think about graphene with electric gates. It can be technically done with ionic gating, but for electrostatic gates, this is not possible. But this will happen quite often when we consider Moiré heterostructures. All right, good. So now we know how is the electronic structure of graphene. So we have Dirac cones. We have an electronic structure that is gapless, that has a Dirac dispersion at low energies. And all this can be accounted for just by considering a single orbital in a honeycomb lattice. So something that is actually very instructive is to see how the electronic structure, especially in two-dimensional materials and especially in graphene, depends on just the geometry that you choose for your two-dimensional material. So let us now focus on a very specific geometry, which is this one. So instead of considering that we have an infinite two-dimensional layer of graphene that has Dirac cones, let's just confine this system. So let's create something like a ribbon. So a system that it's infinite in the x direction, but that it has a finite width. And of course, we can control this width. And eventually, once we make it large enough, we will reach the two-dimensional limit. But if we consider finite widths, we will be in a quasi one-dimensional system. So the basic idea is that this kind of problem can also be described with a tie-binding model in graphene, again, one orbital per carbon atom. And if you take a relatively wide ribbon, the electronic structure that you get now is something like this. So you see that instead of having two bands, you have now many, many more bands. And the reason is because your unit cell no longer has two atoms, but it has all these atoms from the bottom to the top. And well, although you have many more bands, you can see that something like a Dirac dispersion emerges, right? So you have many bands, and in particular, there are two that are like a Dirac-like dispersion. So even though you have a finite system, you still see signatures of these Dirac electrons in this one-dimensional system. All right, this is good, but maybe what is actually more interesting is that if you go to much, much more narrow ribbons, your electronic structure changes dramatically. So for example, if you consider a ribbon that it's very, very narrow, actually your system is no longer a semi-metal. Your system is a semiconductor now, and you have a low energy dispersion that is just a parabolic dispersion. This is still graphene. This is just a ribbon of graphene, but now due to confinement effects, you have a parabolic dispersion. Now, if you make it a little bit wider, you still have a parabolic dispersion and you still have a semiconductor, then suddenly at a certain width, you have a semi-metal, then it becomes a semiconductor again, then semiconductor, then metal, then semiconductor, then metal. And of course, eventually your gap will become smaller and smaller, and eventually you will be a semi-metal. Let me emphasize that in reality, of course, if you account for some effects that this tie-binding model doesn't have, this gapless state actually develops a gap. And this gapless state also develops a gap. So you actually have a gap all the time, and this is just effects that happen at the edge of the armature ribbon. But what is important for us is that just by confining graphene electrons, you get electronic dispersions that are completely different from what you had in the two-dimensional limit. All right, good. So now let us go to the ultimate limit of confined Dirac electrons. So no longer ribbons, but actually just quantum dots of 2D materials, and in particular, quantum dots of graphene. So one of the really important points about two-dimensional materials in graphene, and it's something that I didn't emphasize so far, is that all these confined heterostructures can be grown experimentally with an extremely high precision using chemical techniques. So perfect ribbons can be grown with on-surface synthesis. The same applies for graphene islands and so forth. So even though it seems that when we draw these structures, we are just talking about science fiction structures that we can compute in our lab, in our computer, but don't exist in the lab, all these quantum dots, all the different graphene nanoribbons that you can think about can be synthesized. And this is maybe one of the most important points of this, that this is not just some electronic structure that we can compute. This is something that happens in a lab. So now let's think about the different graphene quantum dots that we can have. So of course, for a quantum dot, we use the very same model. So again, single orbital model in a honeycomb lattice, and we consider a certain confined geometry. So for example, for graphene, it is relatively natural to consider a quantum dot that has a triangular shape. So if you take a quantum dot with a triangular shape, what you actually see is that no matter how big you choose your dot, then you always have a gap. So you no longer have a gapless state anymore. You are going to see a gap for every single island with this edge that you can build. And of course, this gap is a confinement gap. But what this actually tells you is that just by confining graphene, you could, for example, create qubits if you are capable of controlling the electrons in these confined quantum dots. And this can be actually extremely interesting because graphene has an extremely low spin orbit coupling, right? And one of the most, let's say, critical points for qubits is that you can have decoherence, and many of the decoherence effects are driven by spin orbit coupling. So if you are capable of having qubits in a system with very low spin orbit coupling, you can potentially have a very large lifetime for graphene quantum bits. This has not been, let's say, done so far. There are early attempts, but this is, for example, a really powerful application of this confined two-dimensional materials, and specifically graphene for being so light. All right, good. And this is what I mentioned. If you make the island bigger, you still have a gap. And if you make it bigger, you still have a gap. And of course, this gap is going to decrease as a power law as you make the island bigger and bigger, in particular as 1/L, just because you have Dirac electrons. And now that you see these plots, you may already realize that these are actually some of the things that you will be computing in this afternoon. So these plots are directly taken from the examples, and some of the things that you will have to do is to ask a few questions and change the geometry and see how the spectra changes. All right, good. So essentially, this is what I showed you before systematically. No matter how big you make your quantum dot, you still always have a gap. Eventually, the gap becomes smaller and smaller, but you have it all the time. And of course, for qubits, we would like to stay maybe in a limit like this one, because the smaller the gap, let's say, the smaller our coherence time maybe. Yeah, that's a very good question. So in principle, no, this is just a confinement gap. This is a single particle gap. So this gap just comes from, let's say, particle in a box states. So here there are no Coulomb interactions yet. Of course, if one introduces Coulomb interactions, some of these gaps may become bigger depending on the filling that you have. And let's say in some cases, you can even develop a gap purely from Coulomb interactions. But this is not a Coulomb gap. It is just a confinement gap. Yeah, great, thanks. All right, great. And then one more thing of this quantum dot islands, of course, as quantum dots, as finite systems, each individual state is going to have a certain dispersion in real space. It's going to have a certain profile. So the typical profiles that you see in particle in a box states. And this, of course, something that has been also measured experimentally very often, these graphene nano islands. And this is, for example, a very good quality factor to know how clean your edges are. So if you start having some defects on the edges, then you will see that these patterns may change due to these perturbations on the edges. So again, these are some of the things that you will be computing today. And of course, you can not only do triangular islands, but also hexagonal islands that will have slightly different patterns, still confined states. And you can also think about some more complicated island, like a purely circular island. So all these different quantum dots, they have very similar properties. They have usually a gap coming from confinement. They have a gap that depends on the size of the island. And most importantly, these states have a certain dispersion in real space that can be, let's say, very, very useful for, let's say, for probing them and for knowing how good is the quantum dot that you have. And of course, you can also have square islands. And again, let me emphasize that all these islands can be done experimentally. So this is not just something that we can do in the computer, but all these different graphene quantum dots can be done. And something that is actually very inspiring is that this graphene is the very same graphene that we will use for many other things. So for example, for engineering superconductivity or for engineering Turing insulators. What this actually means is that you can have devices that are made of the very same material, just carbon all the time, just graphene all the time, and that in some parts they behave as quantum dots. In other parts, they behave as topological insulators. In other parts, they behave as superconductors, and so forth. And from the material science point of view, that is, of course, something extremely attractive. Using the very same material to make a device that has many different functionalities and that exploits many different electronic phenomena at the very same time.
The properties depend a bit on the edges.
Yeah, these properties will depend a little bit on the edges. So of course, if you have imperfect edges, they are going to change.
And in practice, probably the edges are not.
Yeah, that's a very good point. And many years ago, you were absolutely right. They were not perfect. So the edges of these graphene nanoribbons were very rough. You didn't have something, let's say, as perfect as this. That was, let's say, perfectly unsure here and perfectly unsure there. They had many different defects all over the edge. But now things are completely different. So now with on-surface synthesis, for example, people can synthesize perfect graphene islands or perfect graphene nanoribbons with no defect whatsoever, or with any kind of feature that they want in the except, I mean, hydrogen has to be there for, of course, for chemical reasons, just because otherwise you would have dangling bonds. But hydrogen is, of course, not a problem. But of course, every single atom that is here on the edge needs to have a hydrogen, because otherwise it would have a dangling bond. But yeah, one of the important points is that pictures as precise as this one can be synthesized. This was not the case 10 years ago. It was something that was achieved just a very few years ago. All right, great. So we were discussing so far confinement effects in two-dimensional materials, and in particular in graphene. Let me emphasize that this type of confinement effects can also be exploited in other two-dimensional materials, such as, let's say, dichalcogenites especially. So this type of islands, like this triangular shape or hexagonal shape, can also be done with dichalcogenites, maybe not with such high precision and as clean as with graphene, but they are still doable. Now let us move on to a slightly different topic. And in particular, one of the features that we wanted to exploit in two-dimensional materials and that we mentioned before the break, which is how to control two-dimensional materials by adding defects. So since two-dimensional materials have, let's say, two-dimensional nature, one can actually deposit individual atoms and affect the electronic properties of these materials in a much more severe way than in three-dimensional compounds. So of course, in three-dimensional compounds, you can also try to put some atom on the top, but then you have the whole bulk that is still acting as it was before. And of course, you can try to bombard your bulk with some very high energy, let's say, atom, but first, you may destroy your material, and second, it would be very uncontrollable where your individual atoms are going to sit. In contrast, in two-dimensional materials, you can deposit every single atom in the place that you want with almost atomic precision in many instances, which what this actually means is that two-dimensional materials are way more controllable in terms of defects than three-dimensional compounds. So let us just focus, for example, in this minimal case, so a layer of graphene that is kind of the simplest 2D material with the simplest absorbate. And if you look at the periodic table, well, maybe the simplest absorbate is just hydrogen, right? So if you take this material and you just do a tie binding calculation using the very same model than the one that we used before, what you actually see is that you get a state at zero energy that it's localized right around your hydrogen. So what is actually interesting is that when you put a defect on a material, usually the bound state that you obtain is on the defect, right? So if you put, for example, some dopant in a semiconductor, the state that you get is usually in the dopant. And of course, it leaks a little bit to your semiconductor, but it's usually on your defect. In the case of hydrogen in graphene, what actually happens is your whole bound state is not on the hydrogen. It's not on the carbon atom below the hydrogen, but it's on the carbon atoms that are surrounding them. So, and in particular, this is a really fascinating state because it's a bound state in a semi-metal. It's a bound state not in a metal, and it's a bound state not in an insulator. What this actually means is that this bound state is not well screened because graphene is not a metal, And this bounded state is also not exponentially localized because this is not a semiconductor. And actually, this state is a state that it's even non-normalizable. So it can be solved analytically, but it decays with a power law behavior and some logarithmic correction. So this by itself, it's a bounded state that is completely different from what we see in metals, from what we see in semiconductors. And let me emphasize that this defects in two-dimensional material is something that we will also address several times, in particular when dealing with superconductivity. But then the last point that I want to make is that, of course, this can be done in a lab also. So depositing hydrogen atoms, in particular in graphene and many other different atoms in other two-dimensional materials, is something that has been done systematically in the last few years. And in particular, one can even dream about creating superstructures with these atoms created with atomic precision. So one can actually create artificial crystals just by putting individual impurities in two-dimensional materials. And that is, of course, something that we are going to address during the exercises. And then the last point that it's worth mentioning is how much the electronic structure of graphene changes just with a single impurity, just by putting a single hydrogen atom. So this is the density of states of pure graphene, the density of states of graphene in the absence of an impurity. So you see this V-shape density of states. That is, of course, what you expect from a semi-metal. But then once you put a single impurity in your graphene and you look at the density of states right in the carbons nearby, you can go even a little bit farther. What you actually see is that you have a density of states with a divergence at zero energy. So at high energies, you still have your V-shape density of states. But now at low energies, you have a divergent density of states. And what this actually means is that interactions in this kind of atoms in graphene can give rise to very strongly correlated states just because your density of states is very, very big around this impurity. And of course, this kind of density of states can also be engineered in a completely different way using twist engineering. But that is, of course, something that we will address later on.